My name is Antonio Mesquita. I'm from Brazil. I'm doing my PhD at the Autonomous University of Madrid under the supervision of Enrique Alonso and Victor Aranda in a project about philosophical problems in 20th century logic. So I'd like to thank Pablo Izascon and the PLEXUS project for the opportunity to attend the summer school. And I'm going to talk to you about the Richard paradox, definability, and non-standard semantics. I started my PhD like 4 months ago, so I haven't done much yet. So what I'd like to do today is to tell you one problem I've been working on recently, and what I've developed so far in the hypothesis I'd like to further work on, and then get your reactions and suggestions on it. So I'm going to start with the Richard paradox. We've been discussing the liar paradox in some of the past sessions. The liar paradox is very popular. But I'd like to discuss the Richard paradox, but actually not in the original formulation by Richard, which is a formulation for continuing theory, and it talks about supposed contradiction in set theory. Actually, I'm going to talk about a version discussed by Alonso Church in 1934, which is for number theory, and it actually focuses on the core of the Richard paradox, which is a problem about nameability or definability, depending on how we formulate it, and how formal systems would fail to formalize even number theory. Next slide, please. So I'm going to first talk a little bit about the Richard paradox, then, can you go back, please? Some remarks Church makes on functions, then I'll relate that to Hanking's non-standard models. The idea is to revisit some ideas we can find in Church and Hanking, and try to use that as a contribution for some active discussions on the literature and philosophical logic. So we have start with the Richard paradox. Can you move on, please?
Oops, sorry.
Okay, thanks. So the idea when we want to use a formal system to formalize a given domain is that we want first to represent the objects of that system, and then we want to also be able to prove the truths about those objects. So suppose there's a bijection between the formulas of a formal system and the functions of positive integers, with the idea we should have a definition for each positive integer. So you'd have a formula phi1 for a function f1, supposing there is an enumeration of functions of positive integers, a function f2 for formula phi2 for a function f2, a formula phi3 for a function phi3, and we know this is going to go wrong. Because of Cantor's diagonalization argument, we can show that for any supposed enumeration, can you go back, please? And suppose the enumeration of functions of positive integers, there's a function of positive integers which does not belong to that enumeration. While with formal systems, at least the ones Church's working with, and I think what's usual for formal systems, is to have denumerably many formulas. Can you go on, please? So Church formulates the Richard paradox. He says, the Richard paradox can be said to consist in the following problem. How is it possible that a system of symbolic logic, in which the set of all formulas is enumerable, should be adequate for any branch of mathematics which deals with the members of a non-enumerable set, in particular for elementary number theory? So from the look of this problem, we wouldn't be able to formalize even elementary number theory. So logic as the idea to use formal systems to represent domains of objects would have a big problem, and the logicist project would also be failed. So we basically have two consequences of the Richard paradox. The first, in every formal system for number theory, there are functions of positive integers that are not definable in such systems, such as the function 1 plus fx. So we do not have expressions for every element of the domain. And for every consistent formal system for number theory, there are truths about functions of positive integers that are unprovable in those systems. For example, that either 1 plus fx is a function of positive integers, or that it is not. As we are dealing with classical semantics, this function either is or is not a function of positive integers, but we cannot prove that in this given formal system. So Church concludes, this of course is a deplorable state of affairs. It plainly implies that the whole program of the mathematical logician is futile.
Nice. We know it's no, right?
So we can all go home now.
Yeah, let's die or have a beer.
For in the presence of such a situation, not only is it impossible to obtain a single set of postulates which would lead to all mathematics, as for example the authors of the Principia Mathematica would do, but it is even impossible to obtain a set of postulates adequate to a particular branch of mathematics, such as number theory, analysis, or Euclidean plane geometry. Can you come back, please? This is basically the problem that would have to be solved. We are going to see Church in this paper thinks there's a solution, and then he changes his mind and gives another solution, which you probably already know. But at first, an obvious solution would be just to use non-denumerable formal systems. So the problem is that you don't have enough expressions for representing all functions. We use a non-denumerable system, and then we have one expression for every function, but of course we lose important properties. We basically lose what we want formal systems for. And people like Church, Gödel, and Emil Post also have various critiques to the idea of having infinite symbols, non-denumerable symbols in a language. I'd like to further work on those critiques. But that's that for the moment. The idea is that we're not going to take that path because we lose the nice denumerability property of formal systems. So what's the alternative? So Church makes some interesting claims about functions, which are of course going to end on the ChurchToing thesis, and then that's the idea we're going to get. So in this paper, for instance, Church says, but this function 1 plus fx of x is not in general defined in such a way that it is always possible to calculate its value for a given positive integer x. But surely a function of positive integers which cannot be defined by any means whatever is no function of positive integers at all. So hence it appears to be possible that there should be a system of symbolic logic containing a formula to stand for every definable function of positive integers, and I fully believe that such systems exist. So Church has this particular view about functions of positive integers that is somewhat close to constructivism, but I believe we're still in a classical framework, according to which a function is something you should be able to calculate its values for its arguments. So using that notion, Church here claims he believes it's possible to have a system in which all functions of positive integers which satisfy that description can be represented. And that, of course, can be done through the ChurchToing thesis, which establishes that a function is effectively calculable if and only if it is lambda definable or 2D computable or any of the other equivalent characterizations. So the idea is that in a system that that incorporates the notion of algorithm, like lambda calculus, we would be able to define all functions that are algorithmically definable. So that would be a system in which we have an expression for every algorithmically definable function. So that's that for the idea for Church's views on functions. I'd like to further work. He has more texts I could explore on those points. But the one thing is that at the time Church was working with this, model theory was still under development. and they did not have a formal account of semantics. They had semantics was something intuitive by that time, but some years after that, the development of model theory allows for a mathematical characterization of semantics. So we would also ask what would be a kind of semantics that is adequate for those claims church makes about functions of positive integers. Because obviously standard semantics for second order logic, for instance, does not conform with the things church say. For in standard semantics for classical logic, the domain of functions is the power set of the domain of individuals. And if the domain of individuals is denumerable, the power set of it is non-denumerable. So there are non-denumerably many relations. And church is thinking to work only with denumerably many relations or functions in this case, namely the ones that are algorithmically definable. So the idea could be that we can use Hanking semantics to do that. Hanking is very famous for this paper called Completeness in the Theory of Types, as you already know, in which he defines general models in order to have a completeness result for a type theory. The idea, we can have more than one way to define general models. There's this definition here, which is meant as a temporary definition. There's a discussion about the impredicativity of this definition, and then Hanking develops it in a more formal way later in the paper. There's also an algebraic definition of general models, which Hanking uses in his doctoral thesis. But the idea I want to get to is that the notion of general models used in 1950 might still presuppose the power set of the domain, in that he says, by a frame we mean a family of domains, one for each type of symbol, as follows. D iota is an arbitrary set of individuals, D omicron is the set of true values, true and false, and D alpha beta is some class of functions defined over D beta values in D alpha. If we characterize this, as some people do, by defining D alpha beta as any subset of the power set of the domain, so we don't require that all possible functions of all possible relations over the domain be in the domain of relations, but we require that any subset of it be in the domain, and additionally we require for the general model that all definable relations be in the domain of relations. We are still presupposing the notion of power set of the numerable domain of individuals, and moreover, standard models are still general models. The notion of general models amplifies the class of models. So it includes standard models, but it is not restricted to standard models. It allows other models. So the point is that we are still committed to the notion of non-denumerably many sets and non-denumerably many relations. The idea here would be to use a modification Hanking makes on general models 3 years later in this paper called Some Notes on Nominalism, which is far less known than the previous one, in which he's trying to answer to Quine's criticisms to second-order logic, and the idea that second-order logic is committed to the notion of arbitrary function or arbitrary set. So Hanking's idea is, hence we take up anew the question whether the pure first-order functional calculus L can be enriched to system N by the addition of specific predicates in such a way that the pure second-order functional calculus M can be given an interpretation in which its class variables can be replaced only by the predicates of N. In the next section, we shall show that this is indeed possible. So the idea here is to provide a semantics for second-order logic, which is suitable for nominalism, in this way satisfying clients' objections. And Hanking's way to do that is to enrich a first order calculus with some predicates, and those predicates we add, and then we have the extended system n. The second order calculus will the functional variables can be replaced by predicates in the language n. And as we're talking about systems here, they are all denumerables, so the functions that can be replaced by that can replace second order variables are denumerably many, are finite in this case. So the idea would be to see if we can drop this claim about nominalism and still try to keep the functions at most denumerably many. So this is it for the quotations, and here are two hypotheses I'd like to work on during the project. The first is Hanking's nominalistic semantics provides a semantics adequate to Church's claims about functions, because here we are dealing with finite or at most denumerably many functions. And it would be nice to check if general models can be constructed with a definability closure to avoid commitment to the existence of non-denumerably many functions. And in this case, we can drop the commitment to nominalism. And the idea is that by doing this, this kind of result and this kind of discussion can be useful in some philosophical logic debates, such as the debate on neologicism, carried out mainly by Crispin Wright and Bob Hale, or I've also recently read some papers by José Ferreiros, in which he is discussing arbitrary functions and arbitrary sets, and he's criticizing standard semantics for second order logic in favor of using a Hanking semantics for it that is not committed to non-denumerably many functions. So that's it, thank you.
So I have no big idea about these issues, but I think I mentioned it might connect with I think Oystein Lindeborg work on plural quantification and how to get second order so the expressive power of second order logic via plural quantification. I don't know if this might somehow, and also a super wild suggestion. I don't know if this discussion might have also something to do with the Skolem paradox.
Yes.
So if you can develop a little bit on this. So I think I remember, was it Skolem's paradox related to downward Lorentz-Skolem, right? So
yes.
You can have a theory about set theory, first order set theory with countable domains.
Mm-hmm. You have, I think you have sentences about non-denumerability that can be satisfied by denumerable models. Yes.
Yeah.
Yes, that's certainly a point to develop and to check the precise relation with this formulation by Alonzo Church of the Richard paradox. And thanks for the suggestion on Lindeborg. That's a bibliography I have still to check.
Question, suggestion. So
yes.
Yeah.
Is there any? This is also very naive and vague, but is there any relation between the issue of definability and non-standard semantics and Carnap's problem?
What is Carnap's problem?
So Carnap's problem is that the rules or the entire consequence relation of classical logic does not determine the specific models. As in, so for example, there are functions from the propositional language to the set 0, 1, which are in a particular sense consistent with the consequence relation for classical logic, but which don't satisfy the truth tables.
Oh, I'm not very aware of that.
And then there's a slightly more complicated version for first order theories. And there's a recent, or I think upcoming, about to be published paper by Pedro da Valle Inclán, where he shows that the first order version has in particular fails certain solutions, certain sort of obvious ways to solve it. In particular because not all sets of the domain are necessarily satisfiable if you're using first order logic as opposed to second order logic.
Mhm.
Not all subsets of the domain. I don't know if it's really related, but
Okay, but it would be worth to take a
Mm.
look at that. Thanks for the suggestion.